Welcome back to section 3 of chapter 8. This section we're going to look at the fourth type of conic section, which is the hyperbolas. They look like parabolas, kind of, but they actually have a lot more in common with ellipses, believe it or not. Our learning targets today: we're going to analyze the equation of hyperbola, graph hyperbolas, find an equation of hyperbola satisfying given conditions, solve application problems involving hyperbolas, and solve systems of nonlinear equations, which we actually did a little bit of last chapter. So, first of all, looking at ellipses and hyperbolas, I said they were very similar. So, let's take a look to compare them. Ellipses, the definition, is a set of all points where the sum of the distances from the point to two fixed points is constant. Hyperbola definition is a set of all points where the difference of the distances from the point to two fixed points is constant. So the difference here is whether it's a sum or the difference. Is it m plus n, or is it m minus n is a constant? So we have a point, that distance, minus that distance, and then absolute value, because the positives gives us one arc, the negatives gives us the other, and their arms. So that equals just a constant, whatever the constant is for that particular hyperbola. Ellipses, the equation was x squared over a squared plus y squared over b squared equals 1. That's the general equation. For a hyperbola, basically the same thing, except instead of adding, we're subtracting x squared over a squared minus y squared over b squared equals 1. Ellipses, to find that focal length, that c, it was a squared minus b squared equals c squared. It was very similar to the Pythagorean theorem, except we were subtracting. For hyperbolas, it actually is the Pythagorean theorem. We're adding those two things. Notice in hyperbolas, the foci are on the outside of our vertices, whereas the ellipses, they were on the inside. So let's take a closer look at some of these hyperbolas. We have horizontal ones and we have vertical ones, just like all the other conic sections. The horizontal ones are the ones that open left and right. They look kind of like that. The vertical ones are the ones that open up and down. Neither of these two things are functions. I was about to call one of them a function, but that doesn't work out. But the horizontal, again, open left and right. Vertical, open up and down. We have foci. The foci, again, are outside the vertices, but they're inside, kind of like the parabola. They're inside the curve of the hyperbola. We have vertices. The vertices are right where you'd expect them to be, right at the turning points of the hyperbola, kind of like with a parabola, except we have two of them. We have covertices. Now, these covertices, kind of like with an ellipse has covertices, but notice these covertices aren't actually even on the hyperbola. They're not on the graph at all. They do have meaning. We're going to use them and see what they are, but they're not actually part of the graph, which is kind of weird. We have a transverse axis. That in an ellipse would be the major axis. It's the one that goes in between the two vertices. In an ellipse, the major axis was the longer of the two. That is not necessarily the case in a hyperbola. It could be much shorter, but it's the one that connects the two vertices. The conjugate axis is going to be the one that connects the two covertices. It'll be along that line of symmetry. Well, I guess they're both along a line of symmetry, but it would be the one that separates the two arms. So the conjugate axis goes between the two covertices. And then if we connect those vertices and covertices with a rectangle, we can draw lines through the corners. Those are asymptotes. One of the big differences between hyperbolas and parabolas is hyperbolas are asymptotic. Parabolas are not. Parabolas continually curve up. Hyperbolas go towards those asymptotes. And again, to find the asymptotes, we make a box using the vertices and covertices. That's where we use those covertices, and then connect the corners. So we do it with the vertical ones as well, and that'll help us to draw these hyperbolas. We have distances. That horizontal distance, A, just like with an ellipse. The vertical distance is B, just like with an ellipse. The book kind of switches it, just like with an ellipse. I like keeping the horizontal distance as A, the vertical distance is B. The focal distance is going to be C, just like with an ellipse, and we already saw that a squared plus b squared equals c squared in this case. Our equation, if it's centered at 0, 0, for horizontal, it's x squared over a squared minus y squared over b squared equals 1. If we wanted to move the vertex, we have x minus h, y minus k, just like we have for every single other conic section, and line and everything else.
Taylor Canover, your bus has returned to pick you up. Taylor Canover, your bus has returned.
That's horribly irritating. So we have our h and our k, and that moves the vertex, or the center. For vertical, we get the same things. The difference between horizontal and vertical, it's not which one's bigger, the a squared or the b squared. It's which one's positive. Horizontal, we have x squared minus y squared. Vertical, we have y squared minus x squared. That is the difference. So which one's positive tells you which way it's going. We have a squared plus b squared equals c squared. The asymptotes are, if it's centered at 0, 0, the line's y equals plus or minus b over a times x, because to go from corner to corner, it goes through the center, which is 0, 0. We go up b, we go over a. The slope is always b over a, and that's true here as well, as long as you don't switch the b and the a's. If we wanted to move the center off of the origin, we just change the x and y to x minus h and y minus k. Point slope form, that's all it is. And it's plus or minus, it's both. That gets us both of our lines. Yep, those are the asymptotes, already got that. All right, so what are we going to do with these hyperbolas? Find the constant difference, just like we have with the ellipses and things like that. So we have our two foci, negative 13, 0 and 13, 0, and we have a point 5, 0. So difference equation, negative 13 minus 5 squared plus 0 minus 0 squared minus, because it's a difference, root 13 minus 5 squared plus 0 minus 0 squared. We can combine or do the subtraction. So negative 13 minus 5 is negative 18 squared, and then plus 8 squared. When we square and square root those, we're going to get 18 minus 8, which is 10. So the constant difference is going to be 10. Write equations in standard form. We have center, vertex, and focus. So the vertex is going to give us either our a or our b value from the center. The center gives us our h and our k. The focus gives us a c value, allowing us to find the other one. Being that this one is always changing the y, and it's a vertex, that means it's going to be a vertical. We're going to have y squared over b squared minus x squared over a squared. equals 1. Plug in what we know. The b is 5, so we can plug that in to get 5 squared. And then we can use the 5 and the 13 to figure out what that a is going to be. So we can square those, we can subtract. A squared is 144. So people are like, oh, a is 12. All right, if we're graphing it, that matters. If we're not graphing it, we need a squared in the equation anyway, 144. So we have y squared over 25 minus x squared over 144 equals 1. Notice this one is, that transverse axis is much smaller than the conjugate axis. That's okay. We'll see what that looks like when we start graphing. Here's a graph, write an equation from the graph. So we have a center is 0, 0. We have our distance out to the vertex is going to be 8. We have a distance to the covertex is going to be 5. This is horizontal, so it'll be x squared minus y squared. So we have x squared over a squared minus y squared over b squared. A is 8. No, 7. A is 7. Y is 5, or b is 5. So we can plug those in and square them. X squared over 49 minus y squared over 25 equals 1. Graphing hyperbolas. When I say they're very similar to ellipses, I mean they're very similar to ellipses. So if we have x squared over 36 minus y squared over 49 equals 1, we find the vertices, negative 6, 0, and 6, 0, because the center is at 0, 0. We find the covertices, 0 and 7. The asymptotes, if we need an equation for an asymptote, which it does say we need to find the asymptotes, we have that plus or minus b over a times x, and then graphing it. So to graph this, we start with our center, and then we're going to go, our vertices in this case are horizontal, 2, 3, 4, 5, 6. Make a point. Come on, pen. There we go. There's a point. 2, 3, 4, 5, 6. Our covertices, up and down 7. 1, 2, 3, 4, 5, 6, 7. We're going to make the box connect for our asymptotes. And then we're going to sketch the hyperbola. In this case, it's horizontal, so it's going to be here and here. If it were vertical, we would have done exactly the same thing, except we would have sketched it on the top and the bottom. So let's see how close I was, and I hope that I used 1-to-1 on this one. I guess we're about to find out. Alright, so I'm plotting my points. There's the box. Okay, I did use 1-to-1. You can barely see it because my drawing is so close. Some asymptotes. And then sketching it. Wow. The right one was really good. My left one I missed a bit, but my right one was really good. So that's the process there. So let's do it again, but this time we have a different center. Still horizontal, but our center is now 4, 3. Our vertices from 4, 3, we're just going to go over 3 each way. So we get 1, 3, and 7, 3. Unless you have to find what those values are, you don't need to find them, because you can just start at your center and go over 3 over each direction. Then same thing up or down 8. Our asymptotes, that would be the equations of the asymptotes. It's the plus or minus b over a, and then we have x minus h and y minus k. Notice that the y minus 3 is there, the x minus 4 is there. Like, those pieces go straight into that equation. So we have center 4, 3, 1, 2, 3, 4, 1, 2, 3, our center. And then vertices, we go over 3, 1, 2, 3, 4, 5, 6, 7, go up and down 8. Make our box. Make asymptotes. And then graph it. And again, it's horizontal. So we're going there. If it was vertical, we would have done everything the same, except that it would have been here and here. That would be the difference with vertical, but it's not vertical. So we're not doing the purple. Let's figure out how close I was. So we have the center, we have some vertices, which I was right on in those. We have our box. We have asymptotes. And drawing, sketching it. Again, I'm close on the right ones, but the left ones I'm struggling with today. But again, I am not an artist. I don't expect you to be an artist either. So that's hyperbolas. So what about solving these systems of equations that are not linear? So for solutions, we have different solutions, or different types of equations. When we have lines, we can have two lines, they intersect once. They could be parallel and not intersect at all, so we could get 0 solutions. They could also be the same line, so we could have an infinite number of solutions. So with lines, we have the option of 1, 0, or infinite solutions. When we have things other than lines, we get a lot more options though. If we have a line and a parabola, we could have 2 solutions. See, there's 2 intersection points there. We could have 1 where the line is tangent to the parabola, or we could have 0 where it misses the parabola entirely. So there could be 2, 1, or 0, and that's with a line and a parabola. With an ellipse and a parabola, or an ellipse, a circle and a parabola, we could have 2. We could have 1 where it's just tangent, and that could be a few different places. We could have none if it's just outside of it, and that could happen all sorts of places. In fact, there for a second we had none where it went around. Now, this is why I work from home. Now we have 2, and now we have 4. We could get a total possible 4. So we could have 0, 1, 2, 3, or 4 solutions. Oh, here's 3. Forgot that we hadn't even done that one yet. So 0, 1, 2, 3, or 4 possible solutions. And then if we have like circles and ellipses or hyperbolas and ellipses, it's the same kind of thing. We can get up to 4 solutions, anywhere from 0 to 4. So solving by graphing, we would graph, just like we would always solve by graphing. We graph it, and we see what it is. First, we have to get it into y equals form, unless you're using Desmos. Desmos, you can plug it in however you want. Then we get our graphing calculator, and we're going to enter them in. So y equals, we have negative 3x, and we have negative 3x squared plus 6. And we graph it. We have our line. It's thinking. and the parabola, and here we can see that we have two intersection points. And so to find them, we can go to calc, which is second trace, and we would find the intersection point, 5. When we do this, it's going to ask us some questions. The first is the first curve, so it'll be on y1 instantly, so we can just hit enter. Then it'll ask us for the second curve. It automatically jumps to y2, hit enter, and then a guess. This is where we choose which one we're looking for. So just get close to one of them and hit enter. And it'll give you the intersection at -1, 3. To do the other one, you do the exact same thing, except when it's going to ask for the guess, you go closer to the other intersection point. So we have the first curve, the second curve, and then the guess, we go over to the other intersection point. Enter, and we have 2, -6. So that's how we can find them by graphing. Oh, I missed a comma in there. There, that fixes it. Generally speaking, we're not going to solve by graphing, because I mean that's an estimate more than anything else. But we can solve by substitution. Here we have y plus x equals 17, x squared plus y squared equals 169. We just need to solve for one of our variables, x or y. In the top one, we're going to plug it into the bottom one. So if we solve for y, we get y equals 17 minus x, plug it in, and then we're going to simplify. So the first thing we have to do is do the 17 minus x squared. And remember, that is not 17 squared minus x squared. Don't be that guy. We have 289 minus 34x plus x squared equals 169. It's a quadratic function. Let's move everything over to one side, combine our like terms. We get 2x minus 34x plus 120. We can factor out the 2. We have x squared minus 17x plus 60. So now we need two things that multiply to give us 60 and add to give us -17. And people always think, let's see, 15 and 4, no. 10 and 6, no. Remember that 60 is also 12 times 5. So we have x minus 12 and x minus 5 equals 0. So we can plug them in. Plug them into the line. Because otherwise, when you square root, you get plus or minus. And a line and a circle, which is what these are, will have a maximum of 2 intersection points. So x minus 12 equals 0, and x minus 5 equals 0, so x equals 12, x equals 5. So plug them into y minus 17, we get 12, 5, and 5, 12. We have something that looks like this. There's a couple ways of doing it. One, you could subtract the 2 and plug that in. You square and you get a quartic. You get a y to the 4th. Or just solve for y squared. Get y squared equals 8x plus 16. And then plug it into y squared, right? We have y squared there. So you get x squared plus 8x plus 16 equals 100. And then again, it's a quadratic, so we're going to subtract. We're going to factor x plus 14 times x minus 6. So x can equal -14 or 6. Plug those in. So we get -14 plus 2 equals 1/8 y squared, which means -12 equals 1/8 y squared, which means -96 equals y squared, which you should see a problem happening here, right? No, not that you can't square root 96. That it doesn't have to be a nice number. The fact that y squared equals a negative number, that's problematic. Y squared is not going to equal a negative number. So this is one that it doesn't work. That happens. So let's plug in the x equals 6. We get y squared equals 64. Square root y equals plus or minus 8. So we have 6, 8, 6, -8. And you can plug that into both of them, and it'll work for both of them. If you were to plug in -14 even in the x squared plus y squared equals 100, that wouldn't work out, because that's a circle, and -14 is outside of the circle, so it's not going to hit that. And you could also write it as 6, plus or minus 8. You just have to know that that is two solutions. When we get 4 solutions, we could have like plus or minus 6, comma, plus or minus 8. That means all 4 possibilities. Solving by elimination, same basic idea, except we're going to use elimination. So we need one of our variables to be the same coefficient except negative, and then we'll add them together. So here, if we multiplied that top equation by a -1, we'd have negative x squared minus y squared equals negative 20. We can add these together, which would eliminate the y squared. We get 3x squared equals 48. Divide by 3, x squared equals 16. Square root x equals plus or minus 4. Plug that in. Here, it does not matter which one you plug it into, because the plus or minus is going to be squared. It will be positive. So you'd end up with 16 for either of them. And subtract the square root, y equals plus or minus 2. So here we have all 4 possibilities. We have 4, 2, 4, negative 2, negative 4, 2, negative 4, negative 2, which can be written as plus or minus 4, plus or minus 2. What plus or minus 4, comma, plus or minus 2 does not mean is it does not mean 4, comma 2, negative 4, comma to negative 2. It does not mean where we have 4, comma, negative 2, negative 4, comma 2. It is all 4 of the possibilities. Doing a similar one, here we have an ellipse on top and a hyperbola on bottom. We need the same value for each of them, except one's positive, one's negative. We could multiply that top one by 3, because notice the x squareds are here and here. So rearranging them, we have the 27x squared minus 27x squared. That's going to cancel itself out. So y squareds, we end up with 21y squareds equals 189. We can divide to get y squared equals 9. And so y equals plus or minus 3. This one, just like the other one, both values are squared. So when we plug it in, we may as well plug in y squared equals 9. Like, it's not going to matter if we plug in positive or negative 3. So we get 9x squared plus 5 times 9 equals 45. Subtract 9x squared equals 0, which means x equals 0. So we have 0, comma, plus or minus 3. This one ends up only being 2 values because of how it hits. If we looked, we have an ellipse, and then we have a vertical hyperbola, which is going to come and hit and come and hit. Sometimes it's fun to graph these just to see that it's like, oh, hey, my answer actually did work. That's what that thing looks like. And this could be written as 0, comma, plus or minus 3. So that is this third section, looking at hyperbolas, looking at solving systems of equations. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.